possible that you get more frequent heat waves as the climate gets warmer. And an example of an extreme heat wave we had in Europe in summer of 2003, which caused at least 35,000 fatalities, and it was the greatest natural disaster in the past centuries in Europe. This, of course, for one individual event, you can never tell whether it's caused by global warming or not, because this is a statistical game. It's like having loaded dice, and if you throw 1-6 with a loaded dice, you don't know whether this one would have come anyway or whether this is because the dice was loaded. So all you can say scientifically is that the frequency of such events increases. You can't say whether any individual event can be attributed to global warming. That's the same with Hurricane Katrina, for example. I come back to tropical storms, but you can never attribute a single event to global warming because there is too much simple chance in the climate system. This chance is simply weather, which has nothing to do with the long-term trends. So let's look at the longer-term time evolution then. The black curve shows the observed values, that is the summer temperatures in Europe, and you see since the year 1900 you see a shape of the curve very similar to the global mean temperature, also here for the European summer temperatures, and you can see that the summer of 2003 was an extreme outlier. It was quite unexpected. I was shocked when the numbers came in of those extreme summer temperatures there, because it was outside that natural variability range that you expect, and it's still not fully explained what happened there. There must have been some nonlinear feedbacks acting. But I want to point you to this model simulation by the British colleagues from the Hadley Center. This is the red curve, and that's what their climate model does, and it reproduces the past very well, as you can see. Of course, not individual years, because individual years, remember, that's just weather, that's random chance. What a climate model is supposed to do is not predict whether any individual year is warm or cold, but it should reproduce that spread of natural variability, and it should reproduce that long-term trend, and the model does that quite well. You can also see that in the climate model you don't get a hot summer like 2003 anywhere near here. You get the first one that is as hot as that in about 2020 or so. But by the 2040s, a summer like 2003 is just normal, and by the 2060s you hardly ever get such a cold summer anymore. This just gives you a feeling how the extreme temperatures shift when the background climate gradually changes. Now another aspect is the precipitation. Precipitation is even harder to predict than temperatures, even regional temperatures, and in some parts of the world the models contradict, because some show increase, some show decrease in precipitation. But one region where all the models agree that we get a strong decrease in precipitation due to the CO2 warming effect, it's the Mediterranean region. This inset here, that's the model simulation for the end of this century, and it shows a strong drying out of the whole Mediterranean area, Spain, Portugal, Greece, Italy. And on the left, the bigger panel here, this is actually the observed trend over the past 40 years or so, and it shows that what the models predict due to the CO2 effect is already happening. We already observe a drying out of the Mediterranean countries here. And one of the consequences of this increasing drought problem in this region is fires, because the drier it gets, the harder it gets to fight fires. They get out of control, and we had one of the major forest fire disasters last year in Greece, where the historic site of Olympia almost burned down. It was just rescued at the last minute. By the way, I know there are probably some guests from the United States here. The same applies to California. California is another region in the subtropics where all the models say we expect a drying out of California. The data show California is actually drying out, and you get major forest fire problems happening in California in recent years. Another impact of climate change that is simple physics is sea level rise. If you warm the climate, sea level will rise for two reasons. Firstly, warmer water expands, it takes up more space. So that's the thermal expansion component. And secondly, you melt ice that is sitting on land, mountain glaciers and the big ice sheets in Greenland and Antarctica. So additional water flows into the sea. And indeed, sea level is rising. That's what these measurements show. Has risen by about 20 centimeters since the year 1880. And this is also a modern phenomenon. You will sometimes see this disinformation floating around that says, well, this has kind of been going on for thousands of years since the end of the last ice age or something like that. That is nonsense. The geological data show that sea level after the last ice age reached a high stand several thousand years ago and has very slowly been dropping since globally. And also, you know, if this had been going on for thousands of years, 20 centimeters a century, in Roman times, sea level would have been 4 meters lower than now, and you wouldn't understand where the Romans built their harbor walls, etc. They would have been high and dry. And we know from Asterix that they were quite stupid, those Romans, but they were not that stupid. So I actually study climate and Earth history. That's what my research group mostly does, paleoclimate, and that's also what I contributed to the IPCC report. It has a whole chapter on paleoclimate, that's natural climate changes going back millions of years, and they give us a clear warning. You can plot here how past climate change have affected sea level, and this is today. That is, we have a global temperature of about 15 degrees centigrade today, and sea level is here shown on the vertical axis relative to today. That's why today is marked 0 here. Now, if we go back to the last ice age, where I showed you this computer animation movie in the beginning, it wasn't only about 5 or 6 degrees colder in the last ice age, but sea level was 120 meters lower. That's all this big ice that you saw on the continents. That's enough ice to lower global sea level by 120 meters. So that's this point here. If you go back further in time, you come to times with warmer climates. The last time that was the case was the Pliocene 3 million years ago. Was about 2 to 3 degrees warmer then globally, but sea level was about 25 meters higher. And if you go back even further, 40 million years ago, that was the last time the planet was ice-free because it was so warm. And that was only about 4 degrees warmer than now, but sea level was about 70 meters higher because of all the ice having melted. And so you see those fall almost on a line, those points. That's what the Earth history is telling us. Now, the forecast by the IPCC for the year 2100 is about 3 degrees warming, but less than 1 meter sea level rise. And the reason why that is so low, compared to the experience of the past, is that sea level responds very slowly. At least we hope so. So that in the beginning, in this century, we will only see a tiny beginning of a much bigger sea level rise problem that will go on for hundreds and thousands of years after we have stabilized the global temperature again. And that long-term big sea level rise mostly comes from the big ice sheets. Here's the Greenland ice sheet. That alone has enough ice to raise sea level by 7 meters globally. And the glaciologists are telling us if the global temperature increases by 2 or 3 degrees, very likely the whole Greenland ice sheet will go. The only question we can't answer is how fast can it go, but people increasingly think, and I quote Jim Henson here on that, the head of the NASA Climate Institute, that this might only take centuries and not millennia, as we have previously thought. We fear that now because the ice is showing dynamic changes. It's starting to flow much faster, and that's an aspect we cannot simulate in the ice sheet models yet, at least not very well. So there have been some new sea level estimates published in the last year or two, and I show you a couple here. That the most interesting is this one by the Delta Commission. They did an estimate for the year 2200 and for the year 2100. That is a kind of high-end estimate of the worst thing that could happen, and it was ordered by the Dutch government, and it's used by them to plan their coastal defenses. And they put together a committee of 20 sea level experts from around the world that gave their report to the Dutch government just a couple of months ago. And they estimate by the end of this century between 55 and 110 centimeters, and by the year 2200 between 1.50 meter and 3.50 meter of sea level rise. So this is kind of the longer term where we're heading towards, and that sometimes gets lost in the public discussion because of this focus only on the year 2100. 2100 is too short a time scale to understand what the sea level is doing. It unfolds on much longer time scales.
So how big will the Netherlands be if this really happens?
Okay, how small? I will take some questions at the end, but I will answer this one quickly. The Dutch coastal engineers are confident that they can cope with 3 meters of sea level rise. I'm surprised by that, but Holland does have a pretty straight coastline, and they have a lot of experience. They have a relatively short coastline compared to the number of people that live there, so they can afford very expensive coastal defenses. And those conditions are not true in other parts of the world, like Bangladesh, for example. People are simply too poor, and the coastline is not in a good shape where you could easily defend it. Or, example, New York, that I just put up here. This is what a once-in-a-century storm surge does to southern Manhattan. This blue thing is how much it penetrates the street grid of Manhattan. This would be a multi-billion dollar disaster which floods subway stations and things like that. Now today that is statistically once in a century, but after 1 meter sea level rise this will statistically happen once every 3 years if the storm frequency remains the same. And obviously, you cannot cope with such a disaster every 3 years. You can if it happens once in a century. That's why New York is planning these coastal defenses, storm surge barriers, the red ones here. They're not building them or planning them. This hasn't been decided. They're discussing them. The mayor's office has been debating this. And you see how complicated it is. You have a very complex coastline here in New York. They have about 1,000 miles of coastline because of all these islands. And you have to build already 3 storm surge barriers to protect Manhattan. And you still have lots of Long Island here where JFK Airport is, etc., unprotected. You can't really do much there. So many parts of the world, there is no way you can protect yourself against the extra storm surge risk that comes from even 1 meter of sea level rise. Okay, final impact that I want to discuss is the tropical cyclones. This simply shows where they are normally in the last 30 years or so. It's those green areas which are those under at risk from tropical cyclones. You see the red dots, they are mega cities, major population centers that are situated right in the track of those tropical cyclones. And climate change has a double impact on these regions. Firstly, sea level rising, of course, increases the storm surge risk from those tropical cyclones, but also some recent analysis increasingly show that the strength of these tropical cyclones is increasing, especially the strength of the strongest ones, the category 4 and 5 hurricanes or tropical cyclones. This is not entirely settled science yet. There is a healthy debate about this, but this year in Nature, the so far, in my view, best analysis has appeared where they reanalyzed the entire global satellite data set since 1980 with a uniform method to have a really homogeneous data set. And they found that 1 degree warming corresponds to about 30% increase in the number of severe tropical storms in the past over the observed values since 1980. And there is a good physical reason for that, because the energy source of those storms is the warm seawater. That's why they only occur in the tropics. Okay, I'll skip that because I want to come to the solutions, and I also want to leave enough time for a discussion. First of all, who causes the problem? That's also interesting to look at this on the individual country basis. Here, this is a distorted map where the size of each country corresponds to its total CO2 emissions over the past 50 years. And that's why the United States is pretty big here. And Africa, for example, is rather small because they have very low CO2 emissions. The colors are the per capita emissions. So the orange and the red countries are those with very high per capita emissions. You see, for example, that